So, hello everyone. I want to take you back to one of my most memorable evenings as an on-call engineer. It was a warm Tuesday evening. I was at home watching a movie with a pizza in my hand when I got an alert from one of our production systems. That alert turned that warm Tuesday night into a 4-hour-long nightmare. At 1 a.m. at night, after everything is back to normal, my only thought was, this could have been solved in 20 minutes. And my lesson was that even the most experienced responders can make wrong decisions. And those decisions and what causes them will be the topic of this talk. Here's me. So hello everyone, thank you for having me. My name is Boris Cherkasky, and I've been breaking, fixing, monitoring, and building production systems at Riskified for the last 4 years. I am a backend engineer and a production advocate. I love observability, I love scuba diving, and I have a small tech blog that you can find using my hashtag #CherkaskyB. So this talk will be a journey into how our minds work and how it plays tricks on us during production incidents. We will start with the anatomy of the incident response process. Then we'll do an introduction into cognitive biases and heuristics. And the majority of this talk will focus on on real-life examples and how psychological biases got manifested in those production incidents. So a few words about Riskified. Riskified enables top brands to fulfill their maximal e-commerce potential by leveraging artificial intelligence and data to reduce fraud and other financial optimizations. Around 60 billion worth of worldwide e-commerce orders goes through our systems, and it's an exciting time for us. But I want to take you to that previously mentioned Tuesday. The alerts, the incident started with total uncertainty. I got an alert from one of our most reliable production systems, one that failed only once during the last 4 years. I will later learn that this uncertainty is what lets those cognitive biases thrive. So let's start with imagining a hypothetical chart of certainty over time during my incident. I will walk you through my decisions. I've started with going through some metrics, and I've opened the dashboard. I didn't go for logs, and it's a decision, and it happens to be a good decision. I see some irregularities, and my certainty grows. I then get a message from one of our colleagues who reports some partial information that contradicts what I'm seeing, and our certainty plummets. We scratch our heads, we think what to do, and we open a more specific dashboard, and it puts us on the path that one of our dependencies is impaired, and our certainty grows. We then think we know what the root cause is, and we decide to restart an instance. And it doesn't help, and our certainty plummets once again. And this goes on until the incident is resolved 4 hours later. A ping-pong game between certainty and uncertainty. Because of this uncertainty, in each decision point, we are prone to cognitive biases and heuristics, who are supposed to make our decision-making simpler, but in fact, may cause us wrong decisions. So let's start with what cognitive biases and heuristics are. Since I'm not a trained psychiatrist, I'm legally obliged to mention that I'm not a trained psychiatrist. So when talking about decision-making under uncertainty, 2 terms come to mind: cognitive biases and heuristics. To simplify this talk, I'm going to address them both at the more general term, biases, and the actual difference between them is not that critical. Biases are mental patterns. They are shortcuts in decision-making our mind makes to simplify that task. A good analogy will be the branch prediction mechanism within the CPU. It's a calculated shortcut the CPU makes to increase throughput. It works most of the time, but when it doesn't, a bad call was made and we need to roll back to our correct state. Let's start with an example. Let's say you hear a commercial on radio that says this and that insurance offers a loan at the interest rate of 0.5% lower than the bank. Even that small sentence has biases in it, put there on purpose to simplify the decision to take a loan. And in this case, it's the anchoring bias. It's a cognitive bias where individuals' decisions are highly influenced by a particular reference point or an anchor. And in this case, each decision we'll be making around taking a loan will be biased towards the interest rate of the bank. And it's probably not a good one if it's being advertised by the competition. So this was a commercial. But what happens in production? Before we dive into this, I think it's important to mention that cognitive biases will come to life in our weakest point, an incident. There's no way around it. What we can do is to limit their effects and volumes by preparing for them early on in our development process, by designing bias-proof systems, maintaining bias-aware environments with every feature and change we deliver to production, using effective alerts and monitoring, and create bias-reducing response procedures. By applying the measures I'm about to discuss, you can benefit in faster incident resolutions, lower frustration within the response team, and maybe you'll get to your pizza while it's still warm. The incidents you're about to see were managed by trained professionals. Do not try them at home. Those are real-life incidents where our response team got blindsided by a bias that affected their behavior. The first incident is the one when one of our most critical data sources failed. The backup didn't work well enough, and our whole business process came to a halt. I'm sure you have a similar process in your system too, is one that's composed of many steps, and each one of those steps can fail independently. One of our responders suggested we disable that data source altogether. And in the fog of war, it sounded like a solid idea. It will get our system back to life. The first time we tried to turn off that data source, it was 30 minutes into the incident, and it was one of the analysts that mentioned it will breach SLAs for one of our top customers. The second time was 50 minutes into the incident, and it was the head of engineering that mentioned it will cause downstream pressures on other systems. The more this idea floated the room, the more stakeholders spoke up about the implication it will have, from accuracy to latency to legal and operational. This was just frustrating. No one could make the call, while in the background, our whole business process is impaired. About 2 hours into that incident, the idea escalated to our chief of operations, who made the call. We cannot turn off that data source. Let me clarify. We had 2 options. The first one was to do nothing and wait for the underlying issue to resolve and have no service availability. The second thing was to turn off that data source and have multiple issues around accuracy, SLAs, and other. Both alternatives are bad. We just didn't know which one is worst and needed our COO to decide. Our response team was paralyzed. No decision could be made. This is the analysis paralysis, and it's manifested in our inability to make that call to turn off that data source. Analysis paralysis is a psychological effect where the more knowledge we have about something, the harder it is to make a decision. All alternatives and outcomes are being weighed without coming to a conclusion. And in our case, the incident was that major that the response team was huge, and it took more than 15 people 2 hours to make that call. My response team wasn't independent in its decision-making. So how can we give my response team its independence back? It's not always possible, but if we start early on in the requirements and the design phase of our systems, we can define an order of priorities for our SLIs, a pyramid, let's say. When the priorities are explicitly defined, the SLIs at the top of the pyramid will always be sacrificed to secure the SLIs at the bottom of the pyramid. And the response team is free to make fast, independent decisions. In my case, it will be explicitly stated that the accuracy is the most important SLI. And we would have known that we cannot sacrifice accuracy by availability. This is what happens if we designed our systems correctly, how we can mitigate later incidents. Now, let's talk a bit about how we deliver features and alerts. The next incident is all about one single alert, this one. It's a pseudo-Prometheus query language, and I'll give you a few seconds to look at it. Let me grab your attention back. You're now as confused as I was. It's 10 in the evening. I know there's an issue with the service's latency, and I mean what appears to be a math lesson. It's been 10 years since I last saw standard deviations. I have no idea what two standard deviations are. By the way, by the raise of hands, how many of you do know what two standard deviations mean? That's a good result. Nice. So I start this incident by Google and Wikipedia to try to understand this alert. So how did I get here? How this alert find its way to production, but I have no idea, not what to do with it, but what it means. My surprising midnight math lesson is a result of a bias called the curse of knowledge, or the knowledge bias. And it has three main effects. The first one is the tendency to assume knowledge one possesses is common knowledge. The author of my alert thought it's common knowledge that two standard deviations under normal distribution are the 95th percentile. And in fact, my alert is P95 latency increase. The second is the inability to roll back to your unknowing state. And this is why teaching is so hard. This is why getting responders to be experienced and confident in production, it's a challenging task. And the third effect is predicting another person's actions is highly biased towards one's knowledge of the issue. And this is why writing runbooks is hard and why so many runbooks are so bad. This is why runbooks, you meet in production runbooks that have missing steps, implicit knowledge, and generally written like nobody else can read them. So how can we mitigate this? We obviously want all of our responders to be experts. Knowledge is a good thing. To mitigate the curse of knowledge, make sure your alerts and monitoring layer is done by the average responder. In other words, normalize the expertise level you need to the one you have. Make your expert train them, review their work, but avoid having this one or two monitoring persons in your teams. If complex alerts and monitoring cannot be avoided, document them thoroughly, again, by the average responder, and let your experts level up the whole organization. Don't let your responders learn during incidents alone. We touched how writing alerts and monitors can be avoided by biases, and in the next example, I'm going to dive even deeper into monitoring and alerting. The next example, and the next incident, is my most painful production incident that I ever responded to. I remember it till this day. It was so painful that I later learned it has two biases that affected my personal behavior in it. And we're going to talk about them one by one. But first, let me describe the system at hand. We started implementing a new generation of services in a microservice architecture. To do so, we needed configuration stored in our main database. To do so, we created a small ETL process that exposed those configurations into that shared storage. And all other services could use those. One of those configurations was a mapping of which features are enabled for each of our customers. The incident started with elevated error rates on our API layer. We were rejecting API calls. Some customers were being refused key features of our product. Since I know the system and the alert originated from the API layer, I started to simulate what could be the root cause for this, and I thought the shared storage was in a degraded state. So I've rerun that ETL manually, and it worked for about an hour. I don't know if any of you ever experienced a P1 incident where you thought you solved the issue, and it later came back to haunt you after you notified business and management that everything is back to normal. But this really made me doubt my engineering skills. I gathered up my teammates, and we've started the investigation once again. And about an hour into this, my teammates found the issue, a bug in the ETL process that was dormant for more than a year. My teammates found it, but not me. For that whole hour, I was digging into that shared storage, trying to prove, mostly to myself, that indeed it's in a degraded state. I couldn't hide my surprise, a bug in a system that was working smoothly for more than a year with no scale or any other code change. It was literally among the last things upon my possible root cause list, around cosmic radiation. This incident was a grueling process of checking a long chain of components to get to the root cause. The alert originated from the actual degraded SLI, but the root cause was up farther downstream. So why did I duck up so deep into that shared storage? Why couldn't I see I'm on the wrong path? I was deeply affected by the simulation bias. The simulation bias states that one's judgment is highly biased towards information easily imagined or simulated by them. And I was simulating a database issue. It's important to mention that simulation is subjective. What I can imagine, probably others can. This is why I couldn't simulate a bug, and why our data engineers probably wouldn't simulate a database issue. So how can we control what our responders simulate? We first need to understand the problem with this incident. The problem was high surface area between the alert and the system. The alert was at the end of a long chain of components, and each one of those components needed to be checked one by one to get to the root cause. And time spent checking each one of those components is time spent simulating wrong path. So we need to send the responders on the correct path as soon as possible with minimal friction. That means all of our alerts and monitors should be set on every dependency and every key SLI. We rather have 20 specific alerts, simple and specific alerts, than 1 or 2 catch-all alerts on the whole process like I had. If the alert was on the ETL process, I would caught the bug probably within minutes. Secondly, we need to minimize the time to start triage. Time spent without data is time spent simulating wrong paths. So we need to, the incident insights should be pushed toward the responder rather than wait for the responder to pull them manually. Most incident management tools offers those integrations to some extent, and we should leverage them. We're now ready to talk about the final bias that affected me in that incident. I know what you're thinking. I'm an experienced responder. I should base my decision on concrete data. I had that data. I had the data that proves that indeed the database is in a degraded state. How could I prove something that isn't? Easily. I went straight to the database metrics, and there it was, my smoking gun. An increase in CPU and decrease in available memory. In fact, though, my increase in CPU was only 2%, and the decrease in available memory was only 200 megabytes. The access on the dashboards were dynamic, but I missed that and rushed into action. So why was it so easy for me, an experienced responder with vast daily mileage of observability systems, to misinterpret what I'm seeing? It comes down to the confirmation bias. We seek information that reinforces our existing positions. We come to a conclusion first, and then we try to find information that fits it, ignoring information and translating ambiguous information in our favor. In my case, it was 2% increase in CPU that made me literally useless during that incident. So how can we mitigate this? First, let's talk about how we show our data. Keep it simple, show simple data. Complex data is hard to manipulate and misinterpret. This includes sensible legends, colors, scales. Arrows should be red. Throughput, as we learned, probably blue and not green. In my case, if the scales were static from 0 to 100, CPU utilization would have been with no visible change, let alone a spike. One more thing about simplicity. Show data with as little dimensions as possible. Dimensions are complex. That same goes with charts with multiple axes on them, elaborate coloring schemes, and in my personal taste, even heat maps are complex. I'm not saying not to use them, but be very aware when you are and why. Next, standardize your data. When the majority of your dashboards looks the same, looking at any dashboard during an incident will feel familiar for the responder, thus reducing the chance for misinterpretation. In my case, I was rarely using CloudWatch for metrics, and therefore I wasn't fully aware that the scales there are dynamic. This is about data. I want to talk about the process. Don't work alone. Just don't. Incident response is a team effort. Try to convince your unconfirmed colleagues and responders that your hypothesis is correct. Draw a concrete line between observed facts, your hypothesis, and the existing production state. Convince them that you are indeed correct. And in my case, if I would have done that, my colleagues would have noticed one of two things. It's either the CPU spike is only 2%, or that the overall CPU utilization was only 25% on a large Redis instance. They would have caught my mistake. This is all the examples I have for you today, but before I finish, I want to show you a small cheat sheet of tips that works for me to mitigate biases before seeing them in production. So keep anything production simple, prioritize your SLIs, use specific alerts and standardized dashboards, and normalize the production status with the average responder. I write here and there about the connection between software and psychology in my blog, and I will be sure to repost those after this talk. And if you found this talk interesting, be sure to check them out. This is it for me. It was absolute pleasure, and thank you for your time.